Okay, so now let's talk about Hamiltonian mechanics of constraints. Okay, so before we talked about this idea of having a constraint manifold M, looking at the tangent bundle to that constraint manifold. So one of the things, of course, one has to deal with, it's like when you're looking at Hamiltonian formulation of that, is that you need to look at the cotangent bundle, which is where the momentum lives. Okay, so we're going to first formally introduce this idea of the conjugate momenta. Okay, so we introduce the conjugate momenta. Okay, which is P, and in the case of most mechanical systems, it's something like the mass matrix times the velocity. Okay, and then more generally, it is the Lagrangian, it's the partial derivative of Lagrangian respect to the velocity. Okay, so this is true. It's this for Lagrangian, which is, for example, half q dot transpose mq dot minus v of q, right? This kind of separable Lagrangian. It's like with quadratic kinetic energy term, right? All right. So maybe I should say that in general, the momentum is this partial derivative of Lagrangian with respect to the velocity, but in the case of it's like a Lagrangian of this form, it's mq dot. Okay, and then you can write the constraint equations. In this form. Okay, so you have q dot is equal to m inverse p, right? And then p dot is equal to negative the gradient of the potential minus this multiplier term, and subject to constraint that q is on the constraint manifold, which I denoted by script m. Okay, and you can derive these equations from an augmented Hamiltonian, right? So this can be obtained from an augmented Hamiltonian. Okay, and I can write it in the following form. H tilde is 1/2 P transpose M inverse P plus V of Q, right, plus a multiplier term G of Q transpose times lambda. Okay. So more generally speaking, it's like if you're in a Hamiltonian, so more generally, right, given a Hamiltonian, H of QP, right, and a holonomic constraint, G of Q equals to 0, right, we can consider an augmented Hamiltonian which looks like H tilde Q of P is the original Hamiltonian HQ of P plus this multiplier term G of Q transpose lambda. Okay, all right, so if you look at this form, it's like we'll look at sort of the more general version of this, right? So this equations what you get, it's like if you start with a Lagrangian of this form, and then you probably know that Lagrangian of this form induces a Hamiltonian which looks like 1/2 P transpose M inverse P plus V of Q, right? More generally, the Hamiltonian is PQ dot minus LQ Q dot. So let me say that Hamiltonian, which depends on Q and P, right, is this subject to the constraint that you're in the image of the Legendre transform, so P is equal to DL dQ dot. Okay, and the reason, of course, why you do this is that if you didn't have this constraint, if you look at the right-hand side, you have something which depends on position, velocity, and momentum, but on the left-hand side, you only have this dependence on position and momentum, so you have to restrict to this image of the Legendre transform, essentially in order to invert this Legendre transform to solve for Q dot, okay? In which you can, of course, do, right? So you can solve for Q dot, and you can write this as M inverse P here, right? It's sometimes the case that you can't invert the Legendre transform, in which case the Hamiltonian looks like the extremisor over the velocity of PV minus L QV. Okay, so that's another way of thinking about this. And if you check, of course, the stationarity condition, it's like for this respect to V is exactly that P is equal to DL dV. So this, if you will, it's like is equivalent to this normal expression, which we oftentimes see when the Legendre transform is invertible. Okay, all right. So, of course, as you might expect, this kind of augmented Hamiltonian can be sort of thought of in two ways. It's more or less coming from the fact that you can write down both Lagrangian and Hamiltonian mechanics in terms of the variational principle, and then you can use sort of the Lagrange multiplier theorem, it's like to add this augmentation term to restrict yourself, it's like to a constraint surface which is on the configuration manifold. Okay, so let's see what happens. So let me just sort of leave this here for now. All right. So, all right. So let me just rewrite the augmented Hamiltonian. H tilde QP is HQP plus GQ transpose lambda. And of course, you can write down the corresponding formulation of the constrained Hamiltonian system. So this induces the following formulation of a constrained Hamiltonian system. Okay, so Q dot is dH dP, right? Maybe I should write this in terms of the gradient. All right, and P dot is minus gradient respect to the potential. Sorry, this respect to Q, it's like of the Hamiltonian, minus G. Okay, and if you recall, G was the Jacobian of the of this vector-valued set of constraint functions, right? And then G of Q is equal to 0. Right. So you have this constrained Hamiltonian system written in this way. And of course, it's like, as I said, it's like this comes from a constraint formulation of Lagrangian mechanics, right? So this comes from Or if you prefer, it's like it also comes from Hamilton's phase-space principle, right? Which is, of course, a variational way of thinking about Hamiltonian mechanics. So anyway, if you're given a Lagrangian L of Q and Q dot, right, with holonomic constraints, G of Q is equal to 0, right, then the solution is given by the arg extremizer. So Q of T is the arg extremizer over curves which satisfy the constraint. Right, so this is what I mean. G applied to the curve, it's like is identically 0, right? And then the integral of this. Okay, and then of course by the Lagrange multiplier theorem, this is equivalent to an unconstrained variational problem, right? For the augmented Lagrangian, okay, where the augmented Lagrangian is L tilde is equal to L Q Q dot, right, the usual thing, minus a multiplier which is time dependent, and the reason of course is that you need to constrain Q at every time, right? So there's a multiplier which depends on time as well, okay? And then G of Q of T. All right. And then once you have that augmented Lagrangian, you can then do the Legendre transform to get the augmented Hamiltonian, right? Then the corresponding augmented Hamiltonian is just given by H tilde Q of P is P Q dot minus L tilde Q Q dot, right? Which is of course P Q dot minus L Q Q dot plus lambda transpose G of Q, right? Which is just H QP plus lambda transpose G of Q, right? Which is sort of the augmented Hamiltonian we had before. Okay. All right. And then you can ask, it's like what the momentum level constraint it's like is, all right? So the momentum constraint, if you will, it's like at the end of the day comes from the cotangent lift, if you will. It's like of the constraint, it's like on the positions. Okay, so the momentum sort of level constraint comes from just the observation that the time rate of change of the constraint function on q of t, right, is identically 0. Well, it's 0 because this thing is identically 0, right? And this is, of course, just g of q times the gradient. Okay, so it's the chain rule, right? You linearize g, it's like to get the Jacobian, and you evaluate it on q. Then you have to differentiate q respect to t, but differentiating q respect to t, right, by Hamilton's equations, right, gives you this term, right? Okay, right, so this is, of course, just q dot. Okay, and then this is, of course, equal to 0. So the cotangent bundle of phase space is given by phase space is given by following. All right, so you denote the cotangent bundle of phase space by T star M. Right, so this is the set of Q and P in R2D, right, with the constraint that Q is in M, which means that G of Q is equal to 0, right? So this imposes the condition that Q is in M. And then the other condition is that this is equal to 0. Okay, so that's G, big G, right, which is the Jacobian of the vector valued function G, which encodes all the constraints, times the gradient of the Hamiltonian respect to the momentum. This thing is equal to 0. All right. Okay. And then we can look at what happens to the energy of the unconstrained system. Okay, so the energy of the unconstrained system is the first integral of the constrained Hamiltonian system. The energy h of qp is of the unconstrained system. As a first integral of the constrained Hamiltonian system. Okay, and how do you check that? You can check that directly by differentiating the Hamiltonian evaluated on a solution of the constrained Hamiltonian system. Okay, so this is just all right. The gradient respect to q of h qp times q dot, right, plus the gradient respect to p of h qp dotted with p dot. Okay, if you prefer, you could have a transpose and then just multiply the two. All right, so this is equal to, so I'm going to substitute the q dot and p dot. It's like from the equations. So this is gradient q h qp, right, gradient p, okay, h qp minus, okay, gradient p h qp dotted with gradient q h qp plus g transpose lambda. All right, so of course this term and this term cancels, right? So this cancels with this piece, and then you're just left with this, right? So this is minus gradient of the Hamiltonian respect to p times g q transpose lambda, right? Okay, but you can okay, you can, it's like see that this term here, right, I'm just going to put this into parentheses, right? This term here is exactly this term, which vanishes, okay? So this is equal to 0 because of this momentum level constraint. Okay, so the constraint that the momentum is in the cotangent bundle, it's like of the configuration manifold, it's like then guarantees that the Hamiltonian associated with the unconstrained system is a first integral of the constrained Hamiltonian system. All right, so let's just stop there.